All right, now I'm recording. Hey, happy Friday, everybody. It's April 5th. We're sketching the graph of secant from cosine. We sketched cosine. Axis points came asymptotes. High stayed high, low stayed low, and they got turned down for what? Now it's on. Okay, okay. I wanted that on camera. That's how I knew I wasn't recording. Turned down for what? We should try that at the next pep rally. You think that'll work? I yell, turn down for what? And all of y'all, wherever you're sitting, start going, yeah. People will think like the bright lights and sound are affecting you. Start talking like that. It looks a lot like the graph of cosecant. Notice that it's only shifted left or right by how much? Pi halves, which is 90 degrees, right? Pi halves is 90 degrees. What do we call two angles that add up to 90 degrees? Complementary. Complementary. If you take the co from complementary, because these graphs only differ by 90 degrees or pi halves radians, and you stick it in front of secant, you get secant and its co-function, its complementary function, what? Cosecant. So the co in all the trig functions, cotangent, cosine, cosecant, stands for complementary. They only differ by 90 degrees from their non-co-functions, okay? Or their other co-functions. All right, what's the domain of this function? It's the set of all x such that x is not equal to. We have a pi halves vertical asymptote plus how often do they occur? Pi. They're pi apart, where n is an integer, so pi n. That's the same domain as what? Same as what? What other function had the exact same domain? Odd pi halves, basically. Odd pi halves. We had vertical asymptotes. No. Tangent. Same as tangent. Same as tangent. Here's another way to remember or to understand why it's the same. Tangent of theta is y over x, and secant of theta is r over x. They are the only two trig functions that have x in the denominator. Yeah? And so they are undefined on the unit circle when x is 0, and x is 0 on the y-axis, which is your pi halves, 3 pi halves, so on and so forth. So that's why they have the same domain. The range of this function, it's the same range as cosecant. It's all set of y's that are outside negative 1 and 1. So negative infinity to negative 1 beefy bracket, union beefy bracket 1 to infinity. Does it have any symmetry? It does. What type? Origin is flip it upside down and it doesn't look the same. If I flip this one upside down, the local minimum at 0, 1 becomes a local maximum. What kind? Which axis? Y-axis symmetry. Yeah, it has y-axis symmetry, which means it's what type of function, even or odd? It's an even function. And so the consequence of that is this. Secant of negative x is the same as what? Bring it out front or forget about it? Forget about it. Yeah. There's only one other trig function that was even. Do you remember which one it was? Cosine, the one that we used to obtain this one, right? If you draw those yellow dots, if you connect them in there, yeah, it's cosine. Cosine is the only other one that's even. So let's make this little notation here, okay? You have even functions, which are going to be cosine and secant. And then you have your odd functions, which are all the others, tangent, cotangent, cosecant, and sine. So every trig function has some type of symmetry. If you have a negative input, you can bring it out front for the four odd functions, or you can forget about it for the pair of even functions, which are each other's reciprocals, cosine and secant. Okay? They all have some type of symmetry. All right, and then the last thing I'll ask you about this, what is the period? What is the period of this? What's that? 2 pi. Just like cosecant, we have to go one up and one down. One up and one down. Okay? And that takes 2 pi radians. So it's a direct consequence of where it came from. It came from cosine that had a period of 2 pi. So its reciprocal also has a period of 2 pi. All right? So there's also Let's talk about the ones that have period of pi. Here's another thing a connection we can make. Period of 2 pi. Which ones have a period of 2 pi? Cosine and secant and sine and cosecant, right? They have periods of 2 pi. Which ones now have periods of just pi? Tangent and cotangent. Yeah, very good. So there's some similarities. You got to make those connections. Yeah, so there you go. There's your new parent function, secant of x. You don't really have to memorize it, do you? Because you already know chala. If you know chala, it is a short stone's throw away to get the graph of secant. All right? Cool. Now, I will ask you to sketch transformations of both cosecant and secant, but it should be an easy task because really all we're going to do is we're going to be sketching graphs of sine and cosine respectively for cosecant and secant. And then at the very end, the last thing we do is instead of connecting the dots with a sinusoid, we do what we did here. We take the axis points, they become vertical asymptotes, highs stay low, and the lows get turned down for what? Ray went beep. He's the only one. He's the only one in the beep. Okay, maybe we'll have to work on that if we want to pull it off. There's one pep rally left this year, by the way, and I'm emceeing it again. I'm happy to do that. No, that's another one. That's a separate one. Yeah. There's a decision day one, and then there's one more that's right before spring fleeing. It'll be probably maybe next week even. I don't know. Yeah, one more, and then we got the decision day one. That's the separate one. All right, let's go ahead and do B. I'm not going to do both of these because we don't need to do both of these, but B is the harder of the two, so let's go ahead and do it. It says to graph this graph of secant, which looks pretty complicated, but here's the thing, right? We're going to pretend to graph y equals 2 cosine of negative pi halves x plus pi plus 1. Why are we going to pretend to graph cosine instead of secant? Because they're what's of each other? Reciprocals, right? And so if I can graph cosine, which we're pros at graphing cosine and sine, aren't we? We spent a lot of time in 5.4 and 5.5 graphing sinusoids. The only thing we have to do at the end is take the axis points and make them VAs, and then turn the highs up and turn the lows down for what? Beep, 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 beep. There we go. That was better. Okay, so let's go ahead and do what we need to do first, which is to put it into standard transformation form. I'll use blue here. So we got the 2 in front. We got the cosine. That's good. But I got to factor out the negative pi on the inside, and the plus 1 is still good. So when I factor the negative pi halves out of the negative pi halves x, I get x. Factoring a negative out of a positive changes the sign. So the question is, what do I get when I factor out a pi halves from a pi? Is it negative 2 pi? Hey, when in doubt, go off to the side on your workbench, okay? We are starting with pi, and we are dividing out a negative pi halves. Remember, factoring out is dividing out. It's what you started with, factoring out divided by what you started with. So put that over 1, and then we can stay, change, flip. My dog was alive again this morning, just FYI. I'll give you an update every day now. Yeah. I think she recovered. I think she just had a fever. Dogs can get fevers, you know. And she was acting like she had a fever. Her underbelly was really, really warm. But she seems fine now. So maybe she's got another few months, a year, 2 years in her. Who knows? She's a spry boxer. She's full of energy. So it's pretty hard to take when she's low energy because it's not. It's like me coming in and just being, Mr. Korpi, are you depressed today? Heck no. Heck no. You'll notice, right? You'll notice if I'm low energy. Yeah. And then you'll wonder if I'm about to die. I'll be like, no, I just got a fever. Why are you here then? Are you contagious? Yeah, I probably shouldn't be here. I'll be here Monday though. I'll be here Monday. Yeah. I don't know how many of y'all will be here Monday, but I'll be here Monday. We'll talk about what we're doing next week here in a little bit. I didn't get a sub. I don't need a sub. I'm going to come on Monday. Yeah. Really? Well, yeah. Well, my kids are grown. I've seen an eclipse on the internet. So, if you pull it up on your screen, it's your better view than being outside. You don't even have to wear glasses when you look at it on your computer screen, a picture of it. Oh, but I'm living it still. It's just out. outdoors and I'm indoors. Well, but I'll be outdoors. I'll be out. I'm taking my 5th period class, however many come, to go watch it. Yeah, and I might take them to the roof out here because I have the key to the fire escape to get out on the roof without sounding the alarm. We'll see. We'll see if we can get away with that. Yeah. Hey, I got a negative input there. Y'all see that? Tom, you see that? The whom, you see that negative I highlighted? I don't want to have to sketch that because that's a y-axis reflection. That doesn't work well for the Chala method. So maybe I can use the symmetry to do something with it. Do I bring it out front or forget about it? I forget about it. I forget about it. Yeah, because it's cosine, which is even. So I get y equals 2 cosine of pi halves times x minus 2 close, close, plus 1. You thought I was describing my closet there for a little bit, didn't you, when I said close, close? Describe your closet. Clothes, clothes, shoes, belts, scarves. I have a few scarves. I don't wear them enough. All right, let's go off to the side and collect our info. A, B, C, D, P, and R. The amplitude is 2. How many cycles do we see between 0 and 2 pi? That's the B value, right? Remember? That's pi halves. That affects the period right away, so let's just jump down to the period. The period is what over B? 2 pi or pi? 2 pi. Yeah, 2 pi over pi halves. Stay, change, flip. The pi's divide out. You get 4. The period is 4. Okay, your C value we're going right 2. Your D value we're going up 1, which means the sinusoidal axis is at y equals 1. And then the range we can get easily. It's going to be y epsilon. The low point is, let's see, how do we get the low point? We go to the D value, which is 1. That's our equilibrium. And we go down the amplitude, which is 2. So what's 1 minus 2? Negative 1, that's our low point. And then our high point is equilibrium 1 up to 1 plus 2 is 3. Yeah, so there's our cute little range. Now, there is a horizontal shift. So we do want to come up here off to the side and make a little sacrificial or rough draft x-axis. There's 0. We come out the length of 1 cycle, which is 4. We bisect it to get 2. And because we count by quarter cycles, we bisect it again to get 1. Oh my gosh. What's the quarter cycle counting interval? 1. Have we ever had such an easy quarter cycle counting interval than 1? We're counting by ones, folks. Can we handle it? 1 many, many, 2 many, many, 3 many, many. We got 1, 2, 3, 4. It's easy. Now, we're moving everything right 2 units. So look at this. We're going right 2 units. We're picking it up and setting it back down in the existing track. It's just going 2 over instead of 1 over. So that's going to be my new starting place. That's going to be my cosine value, which was the high point, remember? If you want, you can even put a dotted line there to represent your new y-axis. But we got to be careful putting a dotted line for the new y-axis because we're going to be drawing vertical asymptotes as well. We don't want to get those confused. But my high point, which was Chala, used to be at 0. Now it's at 2. Okay, so cool. I think we're ready to sketch that puppy. It's primarily positive, so I'll put it a little bit lower than halfway. And since 0 is a critical value, I can just start putting marks. I'll just kind of make them. I'll put 2 on this side, and then I'll just kind of put marks like this, eyeballing it until I run out of room. There we go. And now I got to label them. Oh, this is always the hard part, right? What are we counting by? 1, 2, 3, 4, 5, 6, 7. You can use that tune for anything you want, right? Whether it's Baa Baa Black Sheep, Twinkle Twinkle Little Star, A, B, C, D song, the alphabet song. Those are 3 songs that ripped off the same tune, aren't they? Y'all know which one came first? You would think the alphabet song came first because the alphabet probably predated music, right? But Twinkle Twinkle Little Star came first. Yeah. And then Baa Baa Black Sheep stole it. And then someone said, hey, we could do the alphabet to that too. You know who composed Twinkle Twinkle Little Star? Who? Mozart. Ray knows. You know how old he was?
Oh no, he was like 5.
He was like 5 or 6. Yeah, yeah.
His first
Yeah.
symphony that he ever wrote was like
Twinkle, twinkle, little star, I am Mozart, and you are not. Right. And then we set up the high point of 1, which is about halfway up, and the low point of -1. All right, now I'm going to draw in yellow my new y-axis, which is at 2. Oh, I'm up 1. Sorry, I didn't do my values right. I forgot we were up 1, right? We were up. I did -1. I saw the -1. That's my low point. I'll mark it. That's my low point at -1. I'll say my high point up here is 3, and then the sinusoidal axis of 1 is right in the middle. That was my bad. I'm going to draw that in yellow as well, okay, because it's a temporary thing. So I have the intersection of my new x and y axis, and now I can put the food on the table because the table is set. It's a chala, so we start at 2, 3 with a high point, and then going to the right, it's axis low, axis high, axis low, and axis high. Let's rip off Mozart guy, that guy. I don't know. Now, do we even really need to connect the dots? We don't need to connect them unless you absolutely want to. I'm going to switch to my bold color of purple nurple. Nurple being the only word that rhymes with purple. Try it out. Every point that's an axis point becomes a vertical asymptote. Not the x-axis, but the sinusoidal axis. And then the highs stay high and turn upwards. And the lows stay low and turn down for what? And there's the graph. Now from here, I can ask you all kinds of questions like, what's the domain? It's the set of all x such that x ain't the vertical asymptote. So pick your favorite vertical asymptote. Which one is it? 1 plus, how far apart are they from each other? They're 2 away from each other. So 2n, where n is an element of the set called z, which is the integers. Yeah, absolutely. What's the range? We'll do interval notation here. If the range of cosine was everything between -1 and 3, this range is everything outside -1 and 3. So -infinity to -1, beefy bracket, union, beefy bracket, 3 to infinity. They share the high and low points, -1 and 3. Does this graph have any symmetry? Does. What type? It's an even function, good, which means it has y-axis symmetry. If I would have only moved it over 1 unit instead of 2, I would have had origin symmetry. And if I would have moved it over like a half of a unit, I would have messed up the symmetry altogether. But we moved it over a half cycle, so no big deal. It works. It's like a negative cosine without a shift. We already talked about the periods. So yeah, so that's it. So if you can do that, you're good. Right? Y'all can do that, right? No new skill set needed. We're just piggybacking on skills we've already learned. And then at the very, very end, we just connect those dots in a slightly different way, or use the dots in a slightly different way. Oh, I forgot to turn this one down. For what? There you go. There you go. Thank you. It's going to be an awesome pep rally. It's going to be good. All right. Any questions on that? 5 is a little bit easier. You just pretend it's sine and you pull the negative out front. All right. Let's go ahead and look at this application. There's not a lot of applications out there for these other 4 trig functions, but there are. If you look hard enough, you'll find one, or you might find yourself in life saying, hey, this situation that I find myself in is perfectly modeled by the cosecant function. You may find yourself saying that. Here's one that is perfectly modeled by the tangent function, okay? So we have to take a couple of liberties here. Let's say we have this lighthouse that's stationed 3 miles off this perfectly straight coastline that has this perfectly beautiful sand dune erected so that the light of the lighthouse shines beautifully upon the sand dune. This coastline is perfectly straight, not unlike Padre Island, and it goes on for miles and miles in both directions, okay? Perfectly straight. We can actually measure the distance d that one of these points along the coastline shines as a function of time in minutes, okay? So if we let this be d equals 0, okay, where we are pointing straight at the coast at a right angle, that is distance 0 along the coastline. As this light starts to rotate clockwise in our direction, the distance down the coast is going to increase. Would you agree? I'm not going to use yellow because it doesn't show up that well. I'll use red. So it's shining there. Maybe that's 1 mile down the coast. And then it's shining here. It's 2 miles down the coast. Now it's shining here. It's 3 miles down the coast, so on and so forth. As the light continues to rotate, that distance that it shines down the coast is increasing. Would you agree? Okay. Now, it's going to continue to rotate, and I'll use degrees here so we can understand it. It's going to continue to rotate, and as it rotates, it's getting further and further down the coastline. And would you agree at a faster and faster rate?
Yes.
It has to be, right? What if this is rotated 89 degrees? That's just 1 degree short of 90 degrees. How far down that coastline, assuming the light is bright enough and assuming the coastline is long enough, how far down that coastline do you think that light beam is going to be if I'm just 1 degree short of 90? Close to the very end, like towards infinity, wouldn't you agree? Okay, but here's the kicker. As soon as it hits 90 degrees, as soon as that hits 90 degrees, now it's off the coastline, isn't it? Now it's just shining parallel to the coast. So that's kind of what tangent does. If you think about tangent, let's sketch tangent right here in this little space. Let me move this over. I'll try and line it with the lighthouse. Okay, so here's tangent. It's right here, and it's 0. Okay, this is at t equals 0 minutes. We got minutes on this axis, and we're measuring the distance down the coastline in miles. Okay, let's say we start our stopwatch right at t equals 0 minutes when it's perpendicular to the coast. It's going to increase down the coastline at a faster and faster and faster and faster and faster and faster rate, and then boom, at some point, as soon as it hits 90 degrees, we're measuring our x-axis in time, but as soon as it hits 90 degrees, I'll just mark that as 90 degrees, it's off the coastline again, isn't it? Okay? Now, what's going to happen during the next duration? It's going to be rotating this direction, and it's out at sea, isn't it? It's out at sea. It's out at sea. Okay? So we're not going to see it again. But what happens when it gets just past 270 degrees? What's going to happen out there? It's going to be way down here. And if we talk about this direction as being the positive direction and this direction being the negative direction, where is it going to jump onto the coast down here on the left? At negative infinity. This is to negative infinity, okay? So it's going to look something like this. It's going to jump on at negative infinity, okay? And then it's going to come in and it's going to get back. It's going to get back to 0. And then it's going to do it again. So right there you can kind of tell that the tangent graph is a perfect model for the situation that we have, right? The light beam gets further and further down the coast, approaching infinity. There is no such coastline that's infinitely long, is there? Okay? And the speed at which it's moving down the coastline is also approaching infinity. Wow, that's amazing. And then it shows back up on the other coast, a negative land, just out of nowhere. It shows up, right? It goes right past 270, and boom, it shows up at negative infinity and starts increasing back towards 0. So that's the graph of tangent right there, broken up into 2. Now, let's go ahead and figure out what's specific about this problem. It makes a full rotation every 2 minutes. It makes a full rotation every 2 minutes. So we're not measuring degrees on the x-axis. We're measuring time in minutes. So I need to figure out the period. All right. The period is going to be, let's see what the period is. This is going to be, if it's 2 minutes all the way around, then it's a minute halfway around, which means a quarter way around, it's 30 seconds, right? So from 0 to 90 degrees is 30 seconds, which is a half of a minute. So I can label this right here as 1/2 of a minute. That's 30 seconds. Okay, so from 0 to 1/2 of a minute. So in the first 30 seconds, it's rotating 90 degrees. Is that a fast rotation or a slow rotation? 30 seconds? Like if you stood up right now and you faced the projector, and I asked you to turn to your right and face the water cooler, but I said to do it in 30 seconds. Sir, I've never rotated this slowly before, sir. Usually when you tell me to turn right, I just turn right and I'm there. It's actually rotating kind of slowly, isn't it? It's rotating kind of slowly. But what's happening to the distance down the shore as it rotates consistently slowly? It's speeding up, right? It's going to infinity. If you think a car going from 0 to 60 in 3 point something seconds is fast, this beam is going from 0 to infinity in less than 30 seconds. Wow, that's fast. Okay? So what would be the period then? Well, the period is going to be the distance between two vertical asymptotes, right? Would you agree? The period is the distance between two vertical asymptotes. So I know there's a vertical asymptote right here when it hits 90 degrees, and then there's another full minute right here where it's out at C. 1 minute at C where we don't see it, and then it picks back up over here at another vertical asymptote. So how far is it in between my vertical asymptotes? A minute. Very good. Very good. So there'd be another one over here. That's 1/2 of a minute. This would be 1 minute right here. And this would be 1.5 minutes, so on and so forth. And then it would appear out of nowhere again. And this would be 2 minutes. And then it would go up like this. And that would be 2.5 minutes, 2.5 minutes. We can even go back in time, can't we? Like before we started our stopwatch, that thing was probably still rotating. I can extrapolate backwards now, and there would be another vertical asymptote over here at -1/2, so on and so forth. So let's come down here where our equation is. We need to write the equation. Let's do it right here, actually. The period is 1 minute. The period is 1 minute. So we can actually do, we just finished part A. Now, this is not quite the graph. There's one thing wrong with this graph. We have it starting at 0, and then it's going down infinitely along the coastline. What's actually happening between 1/2 and 1.5? Are we seeing that light beam on the coastline? No, because what? It's where? It's out at C. So this branch, if you want to exit out, this branch is not really of use to us at all. It isn't until minute 1.5 that it picks back up on the coastline and continues. Okay? So it is a graph of tangent. It is a graph of tangent, but we only get to see or apply it every other branch. Y'all see that? Okay, that's kind of cool. But we can still write the equation. Let's write the equation. So the equation, we're going to say d of t, the distance down the coast, is, we're going to need the amplitude, the A value. What's the A value? Let's leave that blank for now. I know it's going to be tangent. How do I find the B value if I know the period? B is what for tangent? Pi over P or 2 pi over P? Pi over the period. So it's pi over 1, which is pi. So it's tangent of pi t, and we're not shifting it up or down at all because we're going straight to the axis perpendicularly. So I just need to know what my A value is. What's the other number in here that we haven't used yet? I've used 2 minutes for a rotation. It's 3 miles offshore. Have I used that yet? Do you think that's the A value? Could that be the A value? Does it have to be the A value? Oh, does it have the A value? So A might be 6?
Oh, I meant it's like 1.5 because
Oh,
isn't like the radius. Never mind.
no, well, yeah, I mean, you're thinking radius, right? The radius, if you want to think about the radius is actually the hypotenuse. You think about the radius. Let's talk about the radius. Let's make a bolder color here. I'm going to go to 5. If I look at this instance right here, if I look at that instance right there, we could call the hypotenuse the radius of this right triangle, right? And the radius is getting bigger. We're actually measuring the horizontal distance on the shoreline. That's what we're calling D. And this is 3. And this is our angle theta right here. And you can call the hypotenuse the radius, which is getting bigger as well. Okay? I want to know what the tangent is, right? So what's tangent of theta when you have a triangle? Well, we're not on the unit circle, are we? So we're going to go back to soaking our toes, right? What is tangent in terms of SOHCAHTOA? It's opposite over adjacent, right? TOA. So from the angle, it's the opposite, which is D, over the adjacent, which is 3. If I solve that for d, which is what we want, I get d equals 3 tangent of theta. Everyone see that? So guess what my a value is? It is 3. Yeah, it's the distance off the shore. Okay, now we could make a note here. We can kind of come up with the domain that we're only interested in it every other cycle. I don't think we need to get into that here. We just understand that we don't see the beam for a full minute at a time while it's at sea. But there's the equation right there. So we got the graph, it's labeled, we got our equation, and now we can start talking about part C. So let's look at part C. It says find d of 1/6. So we'll write d of 1/6, and I'll plug it into my equation, 3 tangent of pi times a sixth. Isn't that pi sixth? It is pi 6. And guess what time it is now, boys and girls? Is it time to grab a calculator? Or is it unit circle time? It's unit circle time. Yeah. So what is tangent of pi 6? Square root of 3 over 3. Y'all know that. You're just being shy. Right, Tom? All right. Now notice what happens to the 3's. That's 3 over 1. So the 3's divide out, so you get the square root of 3 miles. Which I think is 1 point something, right? Would you agree? Square root of 3 is 1 point something. So a sixth of a minute is how many seconds? 10 seconds. Yeah. So in 10 seconds, the beam of light goes from 0, straight perpendicular to the shore, to more than a mile down the shore. That's pretty fast, right? Square root of 3 miles in 10 seconds. That's pretty fast. That's pretty fast. All right, I'm not going to do the others, d of 1/4, d of a third, but you could do them the same way. They come out to be pi 4, tangent of pi fourths, tangent of pi thirds. My point is just to show you is that the distance getting down the shore is getting bigger, okay, faster. And you can see that right here. Tangent is increasing at an increasing rate, okay, approaching infinity. Let's look at part ABC. Let's look at part D. What is the first positive time in minutes that the light beam will be 3,000 miles long? Now, is it possible to have a light beam off a lighthouse visible 3,000 miles down the line? There's no beam big enough or strong enough, unless it's the sun, to actually see that. But in theory, we can make it work. So here I want to know, where is d of t equal to 3,000? So I set it equal to 3,000. Now, you could do one of two things. You could pull out your calculator. You could graph 3,000 and y2 and look to see where it intersects. You'd have to change your y max to something that includes 3,000, wouldn't you? Or you could do it by hand. Let's do it by hand. We know how to do it now. 3 tangent of pi t equals 3,000. I need to solve for t. So first thing I need to do is isolate the tangent of pi t. So I need to get rid of the 3, don't I? So let's divide through by 3, and we get tangent of pi t equals 1,000. And now the magical step that we didn't know of just a chapter ago. How do I untangent something? The inverse. That's where the inverse comes in, or the arc, either one, the inverse or the arc. We're going to learn about the arc in the next section. So the opposite of taking the tangent of something is taking the inverse tangent of something. So we get pi t equals inverse tangent of 1,000. And then I divide through by pi, and I get inverse tangent of 1,000 all over pi. And that's going to be minutes. Now, that's an exact answer. If we want to see what that is so we have an appreciation of it, we can go to our handy-dandy Minnesota calculator. Thank you, Minnesota. If it weren't for you, I'd have to stand up, right, and grab a yellow calculator. I don't know if it's worth you standing up and grabbing a yellow calculator, but if you want to play along with me in the Minnesota realm, you can. I just want to know what that is as a decimal, okay? And so your curiosity could be slaked by my own activity here. I know it's a lot of keystrokes, but you get used to them. Well, I never check them. That's why. They go back 25 years. Loading, please wait. Man, they test your patience here, right? Uh-oh, we have an error. Please contact your administrator. Like whoever does that. Oh, yeah, administrator. I think Minnesota's down. Anyway, you could. Oh, there it is. Right when I was about to give up. I was about to give up, and there it showed up. So I'm going to hit alpha x, and then I go secant tangent. I should be in radian mode of 1,000 divided by pi. Okay, that gives me. Oh, look at this. You're going to like this. 0.499681690 of a minute. That's pretty cool, right? Because we know that at a half of a minute, it's already parallel to the shore and it's off the coastline, isn't it? At 30 seconds, which is a half minute. But notice what happens. Less than 1,000th of a second before it goes off the shore, it's 3,000 miles down the coast. Now, if you think it's fast getting to there, think about how fast it's going to be between there and a half of a minute. In less than 1,000th of a second, it has to go from 3,000 miles down the shore to what? Infinity. That's fast. From 3,000 to infinity in less than 1,000th of a second, that's fast. Okay? And then it disappears off the coastline, way down the coast at infinity. That's the vertical asymptote effect. That's pretty cool. Okay, letter E. Find D of 5/6 and explain the meaning. Okay, so D of 5/6, if we plug it in, that's going to be 3 tangent of 5 pi 6. D tangent of 5 pi 6. Now, if I evaluate tangent of 5 pi 6, y'all know that that's also square root of 3 over 3, but it's negative. So we get negative square root of 3, and that's miles. Now, do negative numbers have meaning here? Is it okay to have negative values here? Absolutely. We said in the beginning that designating a negative number means that you are on the left-hand side of the coastline. Okay, whereas a positive means you're down the right-hand side of the coastline. But are we on the left-hand side of the coastline here? At 5/6 of a minute, let's come up to our graph. 5/6 of a minute is about right here, isn't it? That's at 50 seconds. 5/6 of a minute is just short of 1 minute. Are we even on the coastline at this time? No, we're at sea. So you might think if there were another equivalent of coastline 3 miles back behind us, that we would be square root of 3 miles down that shoreline, but we're not. So we'll just say that the beam is out at sea. He's on vacation, right? He's taking a short respite from his shining on the coastline to just take in the ocean view for a minute at a time. He's working for a minute, and then he's off for a minute, and then he's working for a minute, and then he's off for a minute. Would y'all like that? Come to school for a day and then have 1 day off, and then come to school for another day and have 1 day off? On off, like every other day, on and off? That wouldn't be bad, but then you can't really string a vacation together, right? Because you only have 1 day off at a time. What if we did 1 week at a time? Come to school for a week, get off for a week. Now we're talking. I could probably get behind something like that. My niece goes to Lavernia, and she texts me every Friday, Uncle Kevin, guess what? I'm not at school. And I'm like, shut up. Yeah, they still get summer, but they only go Monday through Thursday, though. And she rubs it in every Friday, like this morning. Uncle Kevin, I'm not at school. Shut up. Shut up, niece. Yeah.
They did that because they didn't have enough teachers.
Is that right? I heard it was to save. You save a lot of electricity too when you shut down buildings. You can actually save money. I don't know because we're not progressive thinkers like that. I think everyone would be behind it. Don't you think so? Yeah.
Except for the school board, because we're still going to school on Monday.
I feel like a game chicken at this point. Like,
I don't know. We don't even get tomorrow or Monday off. So what are we talking about?
I think it's Monday off.
would you like every other
What?
place in the district?
No.
Yes.
And like, how does that work?
I think they go a little bit longer every day. Like instead of 7th period, they just have like 8 periods, or each class is like 10 minutes longer, which I could get behind. Go 1 extra hour a day to have another day off, 3-day weekend. Start a petition. I'll sign it. All right, let's go ahead and do the last one here. A, B, C, D, E, then C. What the heck kind of alphabet is this? I don't know why I labeled the last one C, but it should be F, right? Explain the significance of the asymptotes on the graph on either side of 1/2 and 3/2 minutes. We've already talked about it, so let's just kind of talk about it one more time. The asymptote at 1/2 is when the beam of light goes off the coast to the right-hand side, yes, yes. And then the asymptote a minute later at 1.5 is when it magically reappears where? On the shoreline on which side? On the left-hand side, right? Yeah, that's what the asymptotes represent. I'm not going to write all that out, but that's what they represent. I'll just say F is magically leaving. I didn't say I was going to write it out, but I am. Magically leaving and reappearing. Okay. Now, when we say magically, we mean math magically, don't we? Math magically. All right, so here's your summary. If you want just a summary of the 4 graphs, there they are. Just a couple of things to point out here. Tangent and cotangent have a default period of pi. You count by half cycles. They have vertical asymptotes every full cycle. So the B value is P over B. And cotangent starts at a VA, tangent starts at a critical value. All right, secant and cosecant, default period of 2 pi, just like sine and cosine. They have critical values every quarter cycle, just like sine and cosine. But here's something different. They have vertical asymptotes every half cycle. So you see 2 vertical asymptotes per full cycle. You don't have to know this because you know Chala and Sahala, but secant starts at a high value and cosecant has a VA. I'm going to skip these problems here. These problems, I'm asking you to find the domain without sketching a graph, which requires you to like process. I'm not going to have you do that. If I want you to find the domain, you can make a rough draft x-axis and figure out where your vertical asymptotes are. So I'm not going to have you find the domain without graphing. If you have questions like this on the worksheet, just do it without graphing. I got 2 minutes. I'm gonna summarize what we're doing. I'm gonna put this into a Canvas announcement at lunch. All right. Your worksheet is due Monday at 4:20, not at 9 a.m. That gives those people who are here in class an opportunity to work on it in class on Monday. I'll put this in Canvas, okay? Tuesday, we're having a quiz over 5.6, and then after the quiz, you'll have a practice test assigned to you that's due Wednesday at 9 a.m. And then Wednesday in class, we're testing over 5.1 to 5.6, and your free response question will be a 5.5 question like Mark Twain, okay? There you go. I'll put this in the Canvas announcement so you have it. All right, cool beans. Any questions? All right.